dark and you want to see, you need
electricity, electricity.
Flip that switch and what do you get? You get
electricity, electricity.
Every room can now be lit with just
electricity, electricity.
Where do you think it all comes from, this powerful
electricity, electricity?
Alright guys, hope everybody's doing okay. What we're going to do today is take a look at the last lesson in the entire electrochemistry unit, and that is on electrochemical stoichiometry. So I think it's a pretty easy lesson to wrap up with. Those of us who have missed stoichiometry and doing some of those problems, we get to finally take a look at some of those today and see how it applies to our current unit. So an example of when we would use this is if I had a question like this, where I have an electrolysis of NaCl set up. And I want to figure out how much metal could be plated out and how long it would take. So obviously one of the metal here is sodium would be plated out, right, on one of our electrodes. And I want to actually know if I want to figure out if I let this cell run for a certain amount of time, how much sodium would I actually make, right? Or if I want to make a certain amount of sodium, how long would that actually take me for that to plate out on that electrode? We're going to take a look at that today. So this ties in with Faraday's law. So we're going to be using that Faraday constant that we've used before. The amount of a substance being oxidized or reduced at each electrode during the electrolysis is directly proportional to the amount of electricity that passes through the cell. So we need to figure out how much electricity is passing through the cell. That's going to tell us how much we're going to plate out at either electrode. So this ties in with a lot of the times this is used with electrolytic cells, which is what we had in a previous lesson in this unit. So a couple definitions and some things to get out of the way here first. Don't get too hung up on these because it can get a little bit confusing. But we want to focus on coulombs. Coulombs is the amount of charge transported in a second. Just think of a coulomb as an amount of charge, okay? And we're going to see how that ties in with some other vocab words in a second here. Current, which is what we really need to focus on here, is symbolized by an italicized I. What's the unit for current? Well, current is measured in amps or an ampere, and it describes the flow rate of electricity. So it's charge, which is coulombs, per unit time, which in this case will be seconds. So you want to think of it like the amount of water flowing through a hose. Okay, this would be a small amount of current over here. And then obviously this would be a higher amount of current. There would be more water flowing through the hose per unit time. So current is coulombs, amount of charge per second, unit time. And that's just combined into the variable amp or ampere. So we could, it's kind of like molarity, where molarity equals moles per liter. So you can represent concentration as moles per liter or molarity. This is the same thing. Current could be just referenced as an amp, or what it truly is broken down into, coulombs per second. But the symbol is an italicized I. So to break it apart for you even further, I, which we just said is current, coulombs per second, we represent coulombs by the letter Q. So it's Q over T. Really nothing different than the last slide, other than another representation of coulombs here. What variable could we plug in for that instead of writing out the word coulombs every time? Faraday, we already talked about. That's the amount of coulombs in 1 mole of electrons. So there are 96,500 coulombs per mole of electrons. And then just bringing back our vocab term of a volt and what that is. A volt is 1 joule per coulomb. So we can combine all these things to figure out some stoichiometry problems. All right. We're going to make an extension to our stoichiometry roadmap. It's the last one that we're going to do here, between honors and AP Chem. So, most of this we are familiar with and we know how to use, but I need to make an extension off of here. It doesn't really matter what side you put it on, because you're really only going to be focusing on one element for these. But I need to look at moles of electrons. Okay, that's what we're really focused on with our electrochemical cells, right? How many electrons are moving. So I need to figure out my moles of electrons, and we do that by balancing our redox equations. I need to convert that into coulombs. So I can convert moles of electrons into coulombs using this conversion here, which is Faraday's constant, right? Just defined it here, and we used it already in a previous part of the unit. And once I get my coulombs, I can convert that into time or current, because current is coulombs per second. So if I have some information here, right, either the time or the current or a combination of things, I can go from here into moles of electrons, then into an actual mass, right? I can use my molar mass and convert into the amount that's going to be plated out. So let's see how this all works as we go through a couple example problems. You're going to find it really easy. Before we do anything, we need to have a balanced redox equation. So that is really important. You can't just jump right into this and try to do your stoichiometry without that balanced redox equation, because what are you going to get from that? Well, you're going to get your moles of electrons. Okay, and to go either to the left of this here or to your mass, you need to go through moles of electrons. So you need to have that. Okay, example number 1. What mass of cobalt will be produced in 1 hour with a current of 15 amps? And we want to assume that we're plating solid cobalt from an aqueous solution of cobalt ions. So first thing we have to do is write our redox equation for this. So we're plating out cobalt, right? And we have our cobalt plus 2. Okay, so cobalt 2 plus 2 electrons would obviously give us cobalt solid here. Okay, we know it's 2 electrons because we're going from CO plus 2 into regular cobalt. My mouse is all lost here. There we go. Okay, so that's the next thing we need to do. Break apart some things. Turn hours into seconds. So 1 hour, you can just factor label it. 1 hour gives you 3,600 seconds. And then I like to take my amps or my amperes and break that apart as well. So break apart your amps so you know what units you have within that. And you have 15 coulombs per second. Again, this is just like me taking molarity and breaking molarity up into moles per liter. So I like to see what units I have here within my unit of an amp. So I'm given time and I'm given current. Let's look at my roadmap. Here we are. I'm given time and I'm given the current. So I could use that relationship there between time and current and convert that into coulombs, and then convert coulombs into moles of electrons, and then right into moles of my product, and then mass if I need to go that far, obviously. So let's take a look at it and we'll knock this problem out. So I'm going to set up my factor label steps. You don't know how many steps it is yet. I just have it preset up here so I don't have to keep writing and clicking with my mouse. So we're going to start with time, 3,600 seconds. So what do I want to cancel out? Well, I want to cancel out time, right? So I would put seconds in my denominator, and I want to go into what? Well, I need to get to, if you look at the roadmap here, I need to get to coulombs, right? So I need to have coulombs on top, right? Seconds on the bottom, coulombs on top. So the seconds cancel and I get here. Well, what's my relationship going to be for that? Well, it's easy. I have 1 second on the bottom, 15 coulombs on the top. Look, I just took my relationship here. What's an amp? It's 15 coulombs per second. Since I broke it apart now, I could use it. Cancel out seconds on the bottom, coulombs on the top. This is 15 amps right here. Okay? Amps times seconds gives you coulombs. If you look at the units, they all cancel out that way. Okay, so what's next? I need to cancel out coulombs. That goes on the bottom. And if you look at the roadmap, the next thing I need to go to is moles of electrons. So just use Faraday's constant there for that. And that is 1 mole of electrons on top is 96,500 coulombs on the bottom. So now you can see coulombs canceling out. Next thing you need to do is go from moles of electrons into moles of actual cobalt. So that's an easy step after we wrote out our redox equation. So cancel out moles of electrons and go to moles of cobalt. You can see that 2 moles of electrons right here. Okay. And then just use your coefficients from the equation, right? 1 mole of cobalt. There. Okay. 2 moles of electrons, 1 mole of cobalt. You guys know how to finish it. You convert moles of cobalt into grams. So cancel out 1 mole of cobalt, go to grams of cobalt. Molar mass from your periodic table is 58.69. Knock it out in your calculator, you get 16.4 grams of cobalt. So if you let this cell run for an hour with the current of 15 amps, this electrolysis, you would make 16.4 grams of cobalt on your electrode. So this is how they actually get some of these more reactive elements that are not found, on their own in nature. They can make them through electrolysis, and this is an example of how much they could plate out in a certain amount of time. So it's pretty neat. Okay, we'll do one more together here. So you have an overall reaction of silver going into silver ion going into silver solid. I want to know how many minutes must a current of 5 amps, so my current, be applied to a solution of silver plus. So we have some silver plus solution. And I want to make 10.5 grams of silver metal. So my equation is done for me. I have that written already. What am I given? Well, I'm given a mass. So I'm working backwards here, right? So here I wanted to figure out my mass of cobalt. Now I have the amount of silver I want to make. I need to go and figure out how long that's going to take me. So all I'm doing is going backwards here. I'm given my current, which is important because that's the last link I'm going to need to solve this. So I'm starting here at mass of A. I have my mass of silver that I want, and I want to convert all the way till here, which is my time. So we're just going to go backwards. So let's knock it out. First thing you want to do, break apart amps. So 5 amps is 5 coulombs per second. And, I want minutes here, so I'm going to need to make sure I remember that at the end. So, factor label. See, it's a bunch of steps. I'm going to start with my grams of silver. I have no other choice but to start with that. If I start with my current, I have no way of getting from current into coulombs, right? Because the only way to get from current into coulombs is if I have a time. And I don't. I'm trying to find that for this problem. So, again, start with grams of silver. You just work your way backwards. Cancel out grams of silver and go to moles of silver. So 107.87 from our periodic table. Now remember, you have to go from moles of silver into moles of electrons. So that's kind of like implied here. Okay, like, there's a spot right here where you go from moles or mass of silver into moles of silver, right? And then moles of silver into moles of electrons. So I was trying not to make this too cluttered, obviously, to really confuse everybody. So 1 mole of silver is with 1 mole of electrons. You get that from your balanced equation. 1 mole of electrons, 1 mole of silver. Faraday's constant, 1 mole of electrons on the bottom is 96,500 coulombs of charge. So now I want to get from coulombs into seconds, right? I'm going to use my amps for that. So cancel out coulombs, go to seconds. Notice I just used this, right? 5 coulombs over 1 second is the same as 1 second over 5 coulombs. You can flip that just like you would with molarity, right? Just use that as your conversion factor. 5 coulombs is equivalent to 1 second here. Like that's our relationship. So you could flip it, use it however you need to get what you want to cancel out. We're not done. We want to convert seconds into minutes, and you get 31.3 minutes. So if I want to make 10.5 grams of silver, I need to let this cell run for a little over half an hour with a current of 5 amps. If I want to run it for less time, I would have to increase my current, right? Okay, last example of the lesson here. You guys give this one a try, and then we will see how we did, and we'll go over it. You have to figure out your number of electrons first. So what you have to do here is figure out what's my oxidation number on chromium. Okay, my chromium metal as is here. Any metal or element on its own, in its form like this, is going to have an oxidation number of what? All right, oxidation number of a pure element on its own is 0. Well, what's the oxidation number of chromium going to be here? Okay, you need to figure that out and then figure out how many electrons you need to balance that. Once you figure that out, it's pretty easy sailing from there. Take a second, try to figure it out. We'll go over it. All right, guys, let's take a look at how we did on this. First thing we need to do is figure out our oxidation number on chromium. So you know that oxygen always has an oxidation number of -2. And there are 3 of them. So overall oxidation for oxygen is a -6. There's only 1 chromium, so that had to mean that chromium is a +6. Okay? This is from the very first lesson of the unit where we reviewed oxidation numbers. So what do you have? You have chromium with a +6 going into chromium of a 0. So how many moles of electrons is that going to be? Well, it should be 6, right? So if you write that out, if you just isolate the chromium, take away the oxygen, you have Cr plus 6 plus 6 electrons yields chromium. Solid. Right? So that's what we're going to use in our stoichiometry problem down here. So I have a time, right, of 1.5 hours, and I have my current of 25 amps. So I want to convert all of this into what? I want atoms. All right, so this is a little different than the last one we did because we went to grams on one of our other examples. So no big deal. We're just going to, once we get moles, we're going to go to atoms instead. It's not a huge deal at all. So set up your factor label. Your 1.5 hours is 5,400 seconds. So I didn't show the work for that. I just factor labeled it and got that, right? So I want to convert my seconds into coulombs. So cancel out seconds on the bottom, 25 coulombs on the top. I get that from here. All right, 25 amps is the same as 25 coulombs per second. So I use that conversion how I need to cancel out seconds. Now, since I have coulombs, I go into moles of electrons using Faraday's constant, 96,500 coulombs in 1 mole of electrons. So coulombs cancels out. Now I use this, 6 moles of electrons in 1 mole of chromium. Right, or chromium, right? So takes care of that. Now I go from moles of chromium into atoms. If I wanted to figure out how many grams of chromium I plated out, I would just go from moles to grams and use the molar mass. But since I'm going into atoms, I need to use Avogadro's number, 6.02 times 10 to the 23rd atoms. Pop all that into my calculator. Proper sig figs here. If you're counting the 25 as 2 sig figs, the 5,400 as 2 sig figs. It gets a little weird here, but 2 sig figs, 1.4 times 10 to the 23rd atoms of chromium for your answer there. Okay? That takes care of it, guys. So you're really just using your time and your current or a combination of those or some other information you're given and just doing a stoichiometry problem. The only part that's new is really this part here. Like, how do you get from your time and current into moles of electrons, right? And then just do some stoichiometry here with your coefficients from your balanced equation, and then do what you need to at the end, whether it's atoms or grams, whatever you're trying to solve for. All right, that takes care of Unit 7. So electrochemistry is over. We'll be taking the test soon, and there's some review stuff that we might be working on. So all that will be on the lesson plan roadmap or announced in the next day or two, or the next time I see you guys. So anyway, hope that made sense to you guys, and hope you found it relatively easy to do, and that takes care of today. So thanks, and see you guys later.